We will now start a new chapter. This is called signed measures. So let XS be a measurable space, and let us have mu1, mu2 measures, and alpha 1 and alpha 2 non-negative real numbers. Then you can define alpha 1 mu1 plus alpha 2 mu2 of E in the usual way. This is alpha 1 mu1 of E plus alpha 2 mu2 of E for every E in S, and then alpha 1 mu1 plus alpha 2 mu2 is a measure. This is we have seen it and it's easy to prove. Okay, so now what if alpha 1, alpha 2 belong to R? That means they are not just non-negative numbers. Now, so for instance, if you have mu1 minus mu2, then there's a difficulty is if both mu1e and mu2e are infinite, then mu1 minus mu2 of E is not meaningful. So at least one of them has to be finite, and this kind of situation we already encountered in defining integrable functions. We wanted the integral f plus or the integral f minus to be finite. Of course, when we define integrability, we said both of them are finite, but you can define an integral if at least one of them is finite. In the same way, if you want a measure, at least one of them should be finite. Of course, now the possibility is that at least some sets may have negative values for the measure. So the measure will now, that's why we call them signed measures. So based on all of this, we make the following definition. So XS measurable space and mu extended real valued set function on S. Okay, mu is called a signed measure if 1 mu of the empty set is 0, 2 mu takes at most one of the values plus infinity or minus infinity. That means if at all the set has infinite measure, it will always be plus infinity, or if it will be always minus infinity. You can't have some sets plus infinity, some sets minus infinity, because to avoid the kind of confusion which we mentioned before. 3, mu is countably additive. So if you have these three properties, then you say that mu is a signed measure. Okay, so example, mu1, mu2 measures, one of them finite. Then you have mu1 minus mu2 is a signed measure. Example, XS mu measure space, F integrable real valued function, then nu E equals integral over E f d mu for E in S defines a signed measure. So definition, a signed measure is called finite if mod mu e is less than plus infinity for all e in S. It is called sigma finite if E equals the union of En, N equals 1 to infinity, and mod x x equals the union and mod mu of En is finite for all n. Okay, so then this is called assignment. Okay, so remarks. So sign measure is clearly finitely additive, because you know, as usual, mu of phi is 0, so you can fill in the phi's to make it a countable thing, and by countable additivity it becomes finitely additive. And if mu e is finite, then this implies that if E and E is a subset of F, then mu F minus E equals mu F minus mu E. The same proof as we had for measures, because F can be written as the disjoint union F minus E union E, and by finite additivity mu F will be mu of F minus E plus mu of E, and because mu E is finite, you are allowed to subtract. Okay, so we have this proposition. XS measurable space, mu assigned measure on S. If mu E is finite, let EF in S, E contained in F. Mu F finite implies mu E is also finite. So if you have finite sets, then the subsets will also have finite measure, because mu F equals mu of F minus E union, plus mu E, as we just saw above. Now, even if one of them is infinity, then since you always have only plus infinity or minus infinity, there's no possibility of cancellations, etc. So even if one of them is infinite, mu F will be infinite. So even if one term on RHS is infinite, then mu F infinite, and that's a contradiction, and therefore this implies that mu E finite. So is mu of F minus E, of course. Okay. Proposition XS measurable space, mu sign measure on S. En disjoint measurable sets. Assume mu of union N equals 1 to infinity of En modulus is finite. Then sigma of mu En is absolutely convergent. So proof, we define En plus to be En if mu of En is positive, empty set or greater or equal to 0, empty set if mu of En is negative. En minus equals En if mu of En is less than or equal to 0, and empty set if mu En is positive. Then mu of union n equals 1 to infinity En plus will be equal to sigma n equals 1 to infinity mu of En plus. And similarly mu of union n equals 1 to infinity En minus, because they are the same Ens which you have defined and they are all disjoint, and so by countable additivity you have this is equal to sigma n equals 1 to infinity mu of En minus. Some of these will be 0 in the in between, and the sum of the two series is mu of union n equals 1 to infinity En, which is finite. So this implies both series are finite. But these are the sum of the positive terms and sum of negative terms of a convergent series sigma mu of En. This implies sigma mu En is absolutely convergent. Because the series is absolutely convergent if the sum of the positive terms and the sum of the negative terms independently are convergent. Next proposition, XS measurable space, mu signed measure, En n equals 1 to infinity increasing sequence of measurable sets, then mu of union n equals 1 to infinity En equals limit n tending to infinity mu of En, just as in the case of measures. Similarly, if En n equals 1 to infinity decreasing sequence and mu of Em is finite for some m, then mu of intersection En n equals 1 to infinity equals limit n tending to infinity mu of En. So proof, same as in the case of measures. Since subsets of sets of finite measure are also finite and subtractive property holds. So you can just copy that proof. Everything is true, everything is justified, and therefore we need not go ahead further. Now we make an important definition. So XS, measurable space, mu signed measure, E, measurable set, subset of X. So we say that E is a positive set respectively negative set if for every F in S, mu of E intersection F is greater or equal to 0, respectively less than or equal to 0. Equivalently, E is a positive set respectively negative set if for every F contained in E, F measurable, mu F is greater than 0, respectively less than or equal to 0. Okay. So a positive set means a set of positive measures and all its subsets have positive measures. And similarly for negative. So remark, empty set is both a positive set and a negative set. Remark, any subset of a positive set respectively negative set is positive respectively negative, because further subsets are all going to have the measures of the same sign. Okay. Any finite or countable disjoint union of positive sets respectively negative sets is positive respectively negative, because if you take any subset of it, of each one of them, its intersection is going to have positive measure or negative measure depending on what the set is, and therefore it will be positive or negative since all the terms of the series are of the same sign. Now if I equals 1, 2, are positive respectively negative, then so is A1 minus A2, because it's a subset and therefore it. So this implies that every countable union of positive respectively negative sets, every countable union can be written as a countable disjoint union using differences, and therefore every countable union of positive sets is a countable disjoint union of positive sets and negative sets similarly, and therefore every countable union of positive respect negative sets is positive respectively negative. Proposition: let XS be a measurable space and mu a signed measure. Bi, I equals 1 to n, a finite collection of negative sets. B equals union I equals 1 to n Bi, then mu B is less than or equal to infimum mu Bi. Sorry, since it's a finite thing, minimum 1 less than or equal to I less than or equal to n. Proof. So B1 union B2 is B1 union B2 minus B1, and this is a disjoint union. So mu of B1 minus B2, B1 union B2 is equal to mu B1 plus mu of B2 minus B1. But B2 is a negative set, therefore this is less than or equal to 0. So this is less than or equal to mu B1. So by symmetry, similarly, mu of B1 minus B2, B1 union B2 is less than or equal to mu of B2. So let's call this star. So star true for n equal to 2. General case follows by induction. And that, so this, we will use this notion of positive sets and negative sets to show that, so one of the aims which we want to do is to say that every signed measure can be written as the difference of two measures, one of them finite, at least one of them finite. And for that we need this decomposition into positive and negative sets, so that the measure will be of uniform sign on that particular part. And then we will show that the original measure can be written as the difference of two original signed measure. It will be written as difference of two measures, one, at least one of them which will be finite. So for that we need this notion of positive and negative sets, and we will look at it next time.